Hi there, this is Math 6, Unit 3, Lesson 1. Okay, we're going to investigate a tall building, the Burj Khalifa today building. And so we begin with a little activity here called estimating height. And the first thing you did in class today is I wanted you to take a look at these three pictures and do some estimation of the height of the Hyperion tree, which is the tallest known tree here based upon some information that was given. And so you have a little discussion in your class about how tall you think that tree might be. And it's hard to really say. I mean, the idea is not to take out a ruler, but to do some estimation based upon what you may or may not know. I initially started by looking at a person here and just saying, well, if this person was about, I don't know, 6 feet tall, let's just say that's pretty tall, but maybe 6 feet, I was kind of wondering first, like, how many people tall is that tree if you do something like that? When I did that the first time, I kind of did some little lines like this and just kind of marked it out there. But every time I did it, it just didn't quite work out very well. I kept getting some crazy numbers that were not even close to how tall that tree actually is. But again, you might do better with that than I did. Again, it's just estimating and you're thinking through some things. I do know back in the day when I used to teach in elementary school that the Statue of Liberty actually has a height, and the height of the Statue of Liberty is about 305 feet. So if we just estimated that at about 300, just to say, let's just go with 300 for now, we at least would know that somewhere about here is 300 feet. Okay, so that was like one thing I looked at there. If I took that tree and kind of chopped it in half, I might chop it in half here, and at least what I notice is that this part, and if I chop it in that part in half there, they all seem to be about the same length. Again, you're just estimating. So if this is 300 feet, then from here to here, I might say that every one of these gaps is about 100 and 100 feet, which would probably estimate this tree to be somewhere at about 400 feet total. And that's the estimate they want you to come up with by doing just some guessing what you think. I just didn't find the person to be very helpful in this case. Knowing this was more helpful, but something you may not know is how tall the Statue of Liberty actually is. But it's something you could look up and try to figure that out. But at that point, you might as well look up how tall that tree is, because if you're going to look that one up, look that one up. Let's take a look at the window washing activity. It says here that a window washing crew can finish 15 windows in 18 minutes. If this crew is assigned to wash all the windows on the outside of the Burj Khalifa, how long will the crew be washing at this rate? So first of all, we know that in terms of our rate, we have our windows and we have our minutes, and that overall the crew is washing 15 windows every 18 minutes. That's the rate at which that is happening there. But in order to answer this question, if I want to find out how long the crew's been washing windows for, what is the information that's missing? Well, hopefully you're saying, I don't know how many windows there are. All the windows. I don't know how many that is. Is this the picture of all the windows? I don't know what that's a picture of. Hard to say. But I don't know what that's going to be. In order to figure that out, though, I would have to do a little bit of work to figure out how many windows can they wash maybe each minute. Okay? Or how long does it take to wash one window? So the question really is, what's the rate for one window? How long does it take to wash one window? And from that, I could use that to multiply it by all the windows, if I ever knew what that was. So what I could do is we could then use this table to say, if I multiplied by 1/15, that would tell me the rate for one window. And again, doing the same thing here, this becomes times 1/15. And so I end up with 18/15 of a minute. And again, if you do the math there on that and work that out to maybe a decimal, that's the same as, I'm running out of space here, 1.2. So about 1.2 minutes is how long it takes to wash one window, 1.2 minutes. So that's a nice rate. It tells me that you can wash one window every 1.2 minutes. Now, to find out how long it would take to wash the whole thing, how many minutes, I need to know how many windows there are. And doing a little research here, I can tell you that there are 24,348 windows in this building. So if we take the number of windows and we multiply it by how many it would take per minute, and we multiply that out, that will tell us exactly how many windows can be washed, or how many minutes it will take to wash that many windows. Okay, so when you multiply that out, what you end up with, if you use your calculator, is 29,217.6 minutes. Is how long it would take to wash that many windows. So 29,217 minutes is how long it would take them. So washing one window every 1.2 minutes. Now in terms of like what you would do, how long would that actually take, you probably aren't going to wash windows non-stop for that many minutes. You'll probably take breaks, things like that. So definitely would take a long time nonetheless. Let's look at the third question, third activity for the day. It says in 2011, a professional climber scaled the outside of the Burj Khalifa, making it all the way to 828 meters, the highest point which a person can stand, in 6 hours. All right, so in 6 hours, they got up 128 feet. So we could do something like this. We could say our time and our height. We know already that this person in 6 hours got up 128 meters. So it's our meters and hours. Got it. Assuming they climb at the same rate the whole way, so our rate's not going to change, how far did they climb in the first 2 hours? Well, to help me figure that out, what I probably want to do is to figure out how long does it take to go for, I could do 1 hour or I could do 2. I'm going to go ahead and find out how high they go in 1 hour, because I like that unit rate first of all. It really helps me use the number more efficiently in other manners. So that's times 1/6. So 6 times 1/6 gets me to 1. So 828 times the reciprocal of 6, 1/6, divided by 6, however you want to say that, gets you a number of 138. So we know that in 1 hour, at that rate, they can go 138 meters up. So looking at 2 hours, 2 hours means I'm going to multiply this by 2 times 2, 138 times 2, and so 138 times 2 is 16, carry the 1, 6 plus 1 is 7, 2 times 1 is 2, so we're going to take 276 meters is how high they can go in 2 hours. Okay, then we take that same information, I can put that in my chart here, and it wants to know how far do they climb in 5 hours. We can continue with our table, again using the 1, I can multiply that by 5 to get to our 5 here, which means again taking 138 times 5, and so 138 times 5 hours is 40, carry the 4, 15 plus 4 is 19, put the 1 up there, and 5 plus 1 is 6, so we would say they can go 690 meters in 5 hours, just like that. The last question says, how far do they climb in the final 15 minutes? Alright, this is a great question because there are a couple ways you could do this, right? We know that it took 6 hours to get there all together. Alright, so what might your approach be? We know the final 15 minutes is what we want to find the rate for 15 minutes. We know that in 1 hour they go 138 meters. We know that to be true. So we want to know the final 15 minutes. There are two ways you could do this. We could say that if I know it takes 6 hours, I could do my rate 138 times, I could do 5 and 3/4 hours, which would be 5.75 is how far they went all together. Then I have to do some subtraction. So that's one way I get an answer here. Then I have to subtract that number from the total, use it, and subtract whatever that's going to be from the total height, 828, and we can see how much they would be in the last 15 minutes. What I chose to do instead was I thought, well, knowing that 15 is a quarter of an hour, I could take my rate of 138 actually and multiply it by 0.25. Why? Because 15 is 1/4 of an hour, which is the same as 0.25. So if I take my hourly rate and multiply by 0.25, that gives me 34.5 meters as a solution. That way it was just much more, a little more direct, because I could do some mental math with that 15 to get a quarter and 0.25 to multiply it out there. This way would work as well. You can multiply by 5.75. That'll give you a number. Then you subtract that number from 828 and you'll end up with the same number that's right here, right? So there's always a couple of ways of approaching a problem, so that's what you have. Let's go one last one today. It says, have you ever seen videos of astronauts on the moon jumping really high? An object on the moon weighs less than it does on Earth because the moon has much less mass than Earth. A woman who weighs 160 pounds on Earth would weigh 30 pounds on the moon. If a boy weighs 60 pounds on Earth, how much does he weigh on the moon? So we have some different rates here basically. We have our Earth weight and we have our moon rate. And we know that for the woman, she was at 160 here and 30 on the moon. So that becomes what we're going to use. That becomes our ratio we're going to utilize to figure out how about this boy. Okay, this boy we know is going to be 60 on the Earth, and we want to find out how much he weighs on the moon. That's our goal. So to do that, a couple ways of doing this, but the easiest way is let's find what our Earth weight's going to be for just simply 1 pound. And that's where we should start. So to go from 160 to 1, we're going to multiply by the reciprocal, 160. So 160 times 1 over 60 is 1. And we'll do the same thing with this 30, right? We'll do 30 times 1 over 160. And when I multiply that out, 30 times 160, if I put it in fraction form, it's 30 over 160. Okay, I can reduce that to 3 over 16, right? And so I have 3 over 16 there. In terms of what that is as a decimal, if you want to use a decimal, you could. That's up to you. A lot of kids like decimals these days, but you can just leave it as 3 over 16. There's nothing wrong with that. That's just fine. Now, to go from 1 to 60, that's multiplying by 60. So to go from 3/16 to the next thing, I'm going to multiply by 60. So let's take this number here and let's multiply it by 60. That's 60 over 1. So we're going to multiply this out. I can reduce in the diagonal, right? 16 goes into, well, at least, let's do this. I know that half of this is going to be 8. Half of that's going to be 30. I can cut that in half again and make that a 4. Cut that in half again and make it a 15. Can't reduce 4 and 15. That's just going to be what it is there, right? No problem. And then we have this 3 right there as well. Okay? So, in our case, we would have, where are we at here? Sorry, I have 15. So we have 45 over 4. Something's not quite right in my math right now. All right, we have, let me go back here. 3/16 times 60 to get up to there. I like that part there. Weird. So we have 45 over 4 is what I have there. 45 divided by 4 is 11.25. Not sure if that's right or not, but we'll put it there. 11.25 is what I have currently. Let me double check something real quick. Something's not quite lining up in my notes, which happens sometimes. I'm okay with that. Let's see, climbing. We have that, and yep, that's what we got. So 11.25 is how much the boy would weigh on the moon. Perfect. Okay, so we're in good shape. And then let's see the next one. It says every 10 pounds on Earth are the equivalent to 4 pounds on Mars. So now we're going to take the Earth and Mars. Alright, if the same woman travels to Mars, how much would she weigh there? Well, the same woman weighed 160 pounds there. So first of all, let's look at the info we have. 10 of Earth is 4 on Mars. So Earth is 10, Mars is 4. This lady was 160. And we don't know what she is on Mars. We'll figure that out there. So to go from 10 to 160, that is a nice one because I can multiply that by 16. Which means I could take the Mars rate and multiply it by 16. And 16 times 4, it's going to be 64. So she would weigh 64 pounds on Mars. Alright, so there's that one, looking good. Okay, so for our summary today, what we would say is that there are many real-world situations in which something keeps happening at the same rate. So a bus stop that's serviced by 4 buses per hour. 4 buses per hour. A washing machine that takes 45 minutes per load of laundry. A school's cafeteria that serves 15 students per minute. So we have these rates that happen in the real world all the time. In situations like these, we can use equivalent ratios to predict how long it will take for something to happen some number of times, or how many times it will happen in a particular length of time, right? And so that's what we're doing. If we know that they can serve 15 students in a minute, we can figure out how many students they can serve in 40 minutes. Or we could figure out if you had 600 students, how long would it take? Either way works for that there. We can do it with a table, which we showed many times here today, or we could even do a double number line and show the same type of thing. Alright, so the double number line can get y'all up to 900 students. So I could change that same info here, right, and put 900 right there, and 60. Just depends on what you're comfortable drawing out, sketching out real quick to show those relationships there. We're going to pause there and give you a few minutes to do your homework, and we'll come back and check it together in just a few minutes. Alright, here we go. An elevator travels 310 feet in 10 seconds. At that speed, how far can the elevator travel in 12 seconds? And explain your reasoning. So I'm going to go ahead on mine today and use some tables. So I'm going to have feet, and we're going to have seconds here. And we're given the initial rate of 310 feet in 10 seconds, right? We know we want to figure out eventually how far it can travel in 12 seconds, right? That's our goal. So I'm going to do this. I'm going to just draw 3 rows here, and I know I want to find out 12 seconds is my goal there. So this is what I'm looking for. So let's first of all turn this into a 1 second. So we multiply by what? The reciprocal, 1 over 10, to get a 1 second, which means I multiply this by the reciprocal, 1 over 10. And so 310 times 1/10 is 31. And now to go from 1 to 12, we multiply by 12. And 31 times 12, do off the side here, 31 times 12 is 2, 6, 0, 1, and 3. So we have 372 is the number that goes there. So how far can we go in 12 seconds? We can go 372 feet. All right. There's that one. Let's look at the next one, number 2. Han earns $33 for babysitting for 4 hours. At that rate, how much will he earn if he babysits for 7 hours? Alright, so here is our money, and then we have hours. That's what we're looking at in this problem here. His current rate is $33 for 4 hours. So let's go ahead and find out how much that's going to be for 1 hour. So to find out how much it'll be for 1 hour, we'll multiply by the reciprocal, which is 1/4, and we'll do the same thing over here. Multiply by 1 over 4. So you're taking money, $33, right? And we're doing it divided by 4. So $33 divided by 4. 4 goes into 3 0 times. 4 goes into 33 8 times. We have 32. Subtract. We have 1. 4 goes into 10. Put our decimal there. 2 times. We have 8. When we subtract, we have 2. Bring our 0 down, we have 20, and 4 goes into 20 5 times evenly, so we're good there. So for 1 hour, he makes $8.25. Okay, so we got that by dividing 33 divided by 4. Now to find out for 7 hours, that's our goal there, we're going to multiply by 7, and we'll multiply that rate times 7. So here's $8.25 times 7. We get 5 and 3, 14, 15, 16, 17, carry the 1, 56, 57, put our decimal there, 2, 1, 2, and we have $57.75 is how much he would make for 7 hours. Great, number 3. The cost of 5 cans of dog food is $4.35. At that price, how much do 11 cans of dog food cost? Alright, so same idea. We have our cost, and we have our cans. Alright, so we know that for $4.35 we get 5 cans. In order to get 11 cans, let's figure out, I'm going to go for 11 eventually, let's figure out how much for 1 can. So we're going to multiply by what? The reciprocal, 1 over 5. Multiply by 1 over 5. 5 goes into $4.35. Put a decimal there. It goes into 4 0 times. Goes into 43 8 times. That's 40. We have subtract. We get 3. Bring down the 5, and it goes into 35 7 times. So 87 cents for 1 can. So we're going to multiply that by 11. Multiply that by 11. And 87 cents times 11 is 78078, and we add, take care of the 1. We have 2 behind the decimal, so we hop 2 spaces, and we get $6. Oops, sorry. We get $9.57 is how much 11 cans would cost. $9.57. Very good. All right, number 4. A restaurant has 26 tables in its dining room. It takes the wait staff 10 minutes to clear and set 4 tables. So 10 minutes for 4 tables. I'm going to just write the word tables here so I can see it all together. 10 minutes for 4 tables. How long will it take to clear and set all the tables in the dining room? So how long will it take them to do 26? Explain or show your reasoning. Okay. So what do we know? We know that we have our tables, and we have minutes. We know that they can do 4 tables in 10 minutes. So again, let's find out how long does it take to do 1 table. 1 table is multiplying by 1/4. So we need to put 10 over 4, or 10 divided by 4, which is going to be 2.5 minutes, or 2.5. Why? Because you have 10/4, which reduces to 5 over 2, which reduces to a mixed number 2.5, which can become a decimal 2.5. So that's how we got there. Now, because we have 26 tables, we know we're going to multiply that by 26. So I'll multiply that by 26 as well. So 2.5 times 26 is going to give us 0, 30. 12 plus 3 is 15. Start with a 0. We have 10, carry the 1, and 5. So we add all this up. We have 1 behind the decimal. So we have 65. So it's going to take 65 minutes to set up all the tables at that rate. So 4 tables every 10 minutes. It'll take 65 minutes to set up 26 tables. There we go. Okay. All right, the next one. A sandwich shop serves 4 ounces of meat, 3 ounces of cheese on each sandwich. After making sandwiches for an hour, the shop owner has used 91 combined ounces of meat and cheese. 91. So we have to figure out how many combined ounces of meat and cheese are used on each sandwich. All right, so first question, it's kind of a building question here. We know that you have 4 ounces of meat plus 3 ounces of cheese, which means there's a total of 7 ounces on each sandwich. Okay, so the table, we would say that there are 4 meat. We would say that there are 3 cheese, and our total is 7, right? Now looking at the next question, it says how many sandwiches were made in the hour. We know we have to come back to this table right here and say, well, I have 4, 3, and 7. Let's just move this table to the right page. Yours is probably a little better than mine is. So we have meat, cheese, and total. We have 4, 3, and 7. And we know that they may use a total of 91 ounces of meat in an hour. So that number goes right there to help us know that, well, if we're doing 7 per sandwich, we need to take this 91 and divide it by 7. The reason for that is we're going to take all the meat and we're going to break it up into 7-ounce segments, right? It's like taking all the meat that we use in a sandwich here, and we know that each sandwich is 7. And so we're going to take the 91 that we have, the whole thing, and we're going to chop this into chunks of 7 to see how many slices we get. This is not accurate, I'm just drawing it there. 7 goes into 9 one time. We subtract, we get 2. 7 goes into 21 13 times. So we know that we're able to make 13 sandwiches in that hour. What does that help me do? Well, it's like this. 7 times 13 is 91. And we'll do the same thing here. 3 times 13 and 4 times 13. So when it comes to the meat, we do 4 ounces for 1 times 13 sandwiches. tells me that there are 15 ounces of meat. For the cheese, I do 3 ounces for one sandwich, times 13 sandwiches, for a total of 39 ounces of cheese. Alright, number 6. Here is a flower made up of yellow pentagons, red trapezoids, and green triangles. The yellow hexagons, we have 1, 2, 3, 4, 5, 6 of those. Red trapezoids, we have 2. And green triangles, we have 2, 4, 6, 8, and 9 of those. How many copies of the flower pattern could you build if you had 30 yellow hexagons, 50 red trapezoids, and 60 green triangles? So, or think of it like this. We have the yellow, we have the red, and we have the green. And what we have present right now in a flower is 6 yellow, 2 red, and 9 green in order to make one of those things, right? So now they tell us, well, you have 50 of these, or sorry, we have 30 of the yellow, you have 50 of the red, and 60 of the green is what you have available. So how many of this combination could you actually make? All right, so when you take a look here, if I was to go from 6 to 30, I can multiply by 5 to get there, right? So 6 times 5 is 30, and I could use them all up. If I did, so I couldn't do any more. If I did try to make 6 flowers, I don't have enough. That would take 36. So I know I can get 5 with just the yellow. What about the other numbers? 2 times 5 is going to be 10, which would mean I'd have some leftover, wouldn't I? Okay, I'd have some leftover. This is not a division sign, just leftover there, right? And 9 times 5 is 45, so I'd have some leftover with those ones too. But I definitely could make 5 copies of the flower, right? And what would I have the most leftover shapes of? Well, here I'd have 50 shapes, I'd use 10, I'd have 40 leftover red pieces, and 60 shapes of green minus 45 I'd use, I'd have 15 of the green. So what would I have the most of? The red trapezoids is what I have the most of there. Alright. And our last one is just kind of looking at some measurement tools just to see matching the first list with the appropriate unit of measurement in the second list. So looking at what would you use to measure each thing. So we have the perimeter of a baseball field. So I'm going to look at some terms here. I have perimeter, I have area, I have volume, I have area, I have length, I have volume, and I have area. Now the size is going to matter too. So first of all, for the length, for perimeter, that's going to be dealing with lengths. So centimeters measures a length. Cubic feet seems to go with a volume. Cubic kilometers, because cubic goes with a volume, meters goes with a length, square feet goes with an area, square inches goes with an area, and square kilometers goes with an area of different sizes. Alright, so perimeter baseball field. My choices are meters or centimeters. Let's go with meters. So let's go there. Alright, that makes the most sense, that one. The area of a bed sheet. Area of a bed sheet. Well, I have square feet, square inches, and square kilometers. So a bed's bigger than inches, so let's go with square feet for that one. Volume of a refrigerator. I got cubic feet, cubic kilometers. Kilometer is like long distance, so let's go with cubic feet. Area, surface area of a tissue box. Area, let's go with square inches for a box. Length of a spaghetti noodle. Our choices for lengths are meters, we already used, and centimeters. Let's go with centimeters. Volume of a large lake. We already did cubic feet. Let's go cubic kilometers because it's a large lake. And surface area of the moon. We got here square kilometers, and we're set to go. Just like that. All right. So that's it for today's lesson. Have a great day, and we will see you next time.